Okay, here we go with another Calc 1 video. Here we're going to be talking about derivatives of functions where the variable is in the exponent. Whenever we have a new kind of function we want to take the derivative of, there's always the same definition we have to come back to. We have to do the limit definition. We want to establish some kind of rule for it. So let's go ahead and do that. Just trying to derive the formula for this for you. Oops, that's not the derivative, that's the limit as h goes to 0 of 2 to the x plus h minus 2 to the x over h. Here's f of x plus h, I just plug in x plus h in for x. And then here's my original function. So that's good to go. So right now, if I plug in h equals 0, I get 2 to the x minus 2 to the x over 0. And that's 0 over 0. And that's not good news. That's not 0, by the way. We just have to do more work to figure out what it is. So let's do some algebra. I do notice 2 to the x is a common factor in the top, so I'm actually going to take that out first. Took out 2 to the x out of here, what am I left with? I'm left with 2 to the h on the first one, because if I distribute that, I have to add the exponents. So I get back here, that's fine. Minus, took out 2 to the x, so I get a minus 1 over h. And then I actually notice this limit only has to do with h, and I have this 2 to the x, which doesn't have any h's in it, being like a constant multiple. And we know we can take constant multiples out of limits. So that's actually what I'm going to do. I'm going to take the 2 to the x out. 2 to the h minus 1 over h. Okay, so this limit still is kind of bad news, because if I plug in h equals 0, 2 to the 0 is 1 minus 1 over h, which is 0. I still get 0 over 0. So it's still bad news. That doesn't mean the limit does not exist, by the way. It still exists. But this is not the important part that I want you to notice. The important part is that I took the derivative of a function and I got back the original function just times some number. I don't know what that number is yet, but it's just, I just got the function back, and it maybe this limit is 2, in which case the derivative of the function is just double the original. Or maybe it's, 1.71. I don't know. In which case the derivative is just 1.71 times the original function. That is really, really, really interesting. So we're going to see how far we can take that. This limit right here, if you graph this function that I'm underlining, you'll see the limit exists at 0. But as it turns out, there's not really a great way right now to evaluate it. So you could use a graphing calculator or approximation techniques to get a decimal out, and what you'll find is that this limit is approximately 0.69315. So that's just a decimal. It's not something we can evaluate right now. And it may not be evaluatable in the sense that it might not be sine of something or cosine of something, or, it might not be square root of something, or, it might not be something nice I can write down. But it is something I can approximate with a decimal. Okay? I hope that idea makes sense to you. So that's the idea. So I got back my original function times some number. Interesting. Now what I'm going to do is I'm going to do the same with another number. I'm going to erase this so I can get myself some more room. How about the derivative of 3 to the x? And you'll see why I'm doing this in a second. The derivative of 3 to the x, same as before, limit 3 to the x plus h minus 3 to the x over h. And then just like before, I'll factor out my 3 to the x. 3 to the x times 3 to the h minus 1 over h. I'll take out the 3 to the x just like I did last time. Three to the h minus 1 over h. If I get some kind of graphing calculator out or approximate it, I can see, for example, I can just plug in h is 0.01 or h is 0.0001 or something like that. I'll get that this limit to a couple decimal places is about 1.09861. That should say 1.09. So I got 3 to the x times this funky decimal. But hold on a second. If I did 2 to the x and I got 2 to the x times 0.6, and I did 3 to the x and then I got 3 to the x times 1.09, there should be a number, maybe it's like 2.5. Maybe it's 2.5. There should be a number in between where this limit ends up being between 0.69 and 1.09. There should be a number which gives me 1 as this limit. In which case, that function has a derivative of itself, because it would give me the original function back times 1, if that limit is 1. So you can do the same thing if you do the derivative of 2.5 to the x. You get, I have to actually plug it in. You get 2.5 to the x, and the limit that you get, I'm skipping the steps in the middle, these steps, but that's okay. The number you get is 0.9163. So it's some number between 2.5 and 3. So for some number between 2.5 and 3, the derivative, I'll call that number a, the derivative of a to the x is a to the x itself. Because there's some number in the middle that'll give me this limit as being 1. Because here I undershot it with 2.5. Here I overshot it. Here's a definition. Definition. The number which makes the number a, which makes this limit so what is it going to be? It's a is the base here. So it's going to be a to the h minus 1. This whole limit is what I want to be 1. I'm going to define a number which makes that to be 1, because I know there is one in the middle. So it's going to be the base always goes here. So it's going to be a to the h minus 1 over h. There's some number which makes that, I can pick an a value which makes that equal to 1 by what I've explained before. We define to be e. This is a definition. I want you to forget everything you've learned about e in high school, in algebra, or pre-calc, because you are incapable of understanding what e is without calculus. The definition of e is a calculus definition. So, the definition means the derivative of e to the x is e to the x times, and then there's that limit, e to the h minus 1 over h. By definition, I'm not proving it, this is the definition, it's between 2.5 and 3. That limit is 1. And so I just get e to the x. The derivative is itself. If you play this back and forth game where you do 2 and 3, and you saw this was too small, and this was too big, and you tried 2.5, we saw that gave you that, what did that give you? That undershot it, too small. You can try something in the middle. You can try 2.75. You'll see that's too big. And this is how you can find decimal places of this number. If you do that over and over and over, you can find decimal places. You'll get it's 2.718281828, and it goes on. By the way, it does not repeat. It's 1828, 1828, but the numbers change after that. That's just all I know. So, everything you learned about E, forget it. Because the definition of E is a calculus one. It is the number which makes the derivative of e to the x itself. So, now that we have this, again, this is by definition. You were doing calculations with e, and you were just told it's this magical number, but nobody told you anything about it. This is what it is. So, because e to the x is a good function, good just meaning it's a fine function to talk about. It's perfectly reasonable. It has an inverse. Define, this is definition, the inverse as ln of x. This is a definition. Let me also be clear. There are other ways to define e and ln x. E to the x and ln x. The number e and the function ln. They all involve calculus, but you can prove that they're actually the same. They end up giving you the same number. They're the same functions, etc. So this is not the only way to do it. There are other ways to do it, but they all involve calculus. So if the inverse is ln of x, that literally means, this is just what an inverse is. If I take ln and then I do e to the x, I get back x. And if I do e and I do ln x, I also get x. So now let's see if we can figure out the derivative of b to the x, where b is any real number, positive. I don't have to go through with the limit definition anymore. What I'm going to do is, now I know I have this as a definition. So I'm going to change this b so it has base e. How do I do that? I'm going to change b as e to the ln of b, because e to the ln's are inverses by definition. That's b to the x. Power to a power I can multiply. E to the ln b times x. And now I know how to take the derivative, because this is a chain rule. The derivative of e to the something is just e to that same something. And then I gotta multiply by the derivative of this inside. The derivative, it looks a little weird, of ln b times x. B is just a number. Isn't it just the coefficient? Isn't it just ln b? Because the derivative of 2x is 2. The derivative of 7/2 x is 7/2. So ln b times x, ln b is just a number. So I just get that number back. So then I get times ln of b. Okay, can I simplify this again? I'll rewrite e to the ln b to the x. Because how do I do that? I just know I multiply the powers when it's power to a power. Okay, e to the ln b is b to the x times ln b. So e to the x is the definition. It's defined to be the function whose derivative is itself. And ln of x is its inverse function. In the next couple videos, we're going to be talking, it'll probably be one video, maybe two. We're going to do some examples, and we're going to talk just a little bit more about derivatives of these kinds of functions. And I'll see you in that one.